Okay, so today we will continue to provide the dictionary between fusion category and fusion ring, and then we will start. This will finish the introduction part, and we will start to talk about things with more details. So before, let me fix a mistake I did last time, in fact. So yeah, here. So last time, no, here, this one. When I provided a basic example of integral fusion ring and categories, I mentioned here I wrote something wrong. I wrote z power g. This is wrong. I already fixed it. It's zg, the group ring. So zg is a group ring. This should be fixed like that. And the other example is a character ring like that. So where the basis here is a irreducible character, and here the basis is the element of the group. So there is no confusion. It's really the group ring. Sorry about that. Okay. So dictionary between fusion categories and fusion ring. So the fusion category is an abelian category. So you have an abelian structure. Particular, the consequence of an abelian structure is the existence of a direct sum. And here, so a direct sum of two objects correspond at the level of fusion ring at just the addition. It's a monoidal category, so you have a tensor product, which corresponds to the usual product in the fusion ring. Okay, so what next? What about, so you have some axiom of a monoidal category. For example, you have the associativity constraint. Associativity constraint, which is a natural isomorphism. So for all, you have a natural isomorphism and written as a family of isomorphism like that. So between X tensor Y tensor Z, X tensor Y tensor Z. So natural isomorphism satisfying the Pentagon axiom. So this corresponds to the associativity, the usual associativity. Associativity in the fusion ring. So BI, BJ, BK equal BI, BJ, BK. Okay. What about next? You have the unit axiom. Correspond to the unit here. So B1 BI equal BI B1 equal BI. Okay, so this is done for monoidal. What about next? Finite. What about finite? So let me recall. So we are here. A fusion category is a K-linear, abelian, finite, semi-simple, rigid, monoidal category, such that unit object is simple. So abelian, monoidal, we provided the correspondence with fusion ring. So what about finite? So finite. So finite here correspond to Okay, so here we can correspond to the fact that the basis is finite, finite basis. So in the category framework, it means that you have finitely many simple objects up to isomorphism, and finiteness also in the categorical framework correspond to the finite dimensionality of the Hom space, which here you can see it as a fact that the fusion coefficient are integral like that, which correspond to this correspond to finite dimension of the Hom space Hom C xi tensor xj xk. Okay, so xi tensor xj xk. So the one assumption finiteness for category is finite dimensional Hom space, and here the dimension of this Hom space are precisely of this Hom space, precisely the fusion coefficient. Okay, next point. The unit is simple. So correspond to the fact that B1 is in the basis. B1 is in the basis. Rigid. So rigid, which means existence of dual. So dual of each object, which is existence of two morphism, evaluation map x star tensor x21, co-evaluation map 1, 2 x tensor x star plus zigzag relation. Zigzag relations. So this is rigid, and this corresponds to the dual axiom in the fusion ring level, which is nothing but ni star j1 equal nij star 1 equal delta ij. So you see I star j1 correspond to that. So this Hom space is one-dimensional, and in fact, for A equal G, and in fact, at the categorical level, and it is generated by this fx. Okay. So you can put here, if you want, the anti-involution. In fact, this anti-involution axiom should be assumed as an axiom at the fusion ring level, but at the categorical level, it can be deduced from the rigidity. Okay, now abelian semi-simple. Correspond to abelian, semi-simple means every object can be decomposed into a direction of simple object. here you can see it at the fusion ring level. Every product decomposed as a sum of element of the basis. So you have Bi, Bj equals sum of Nij, K, Bk. So if the product corresponds to tensor product, so you have at the categorical level, by semi-simplicity, every tensor product decomposed, so you can see one correspondence. And in fact, yeah. So the fact that it is semi-simple at the categorical level, at the fusion ring level, so you have a basis, so any element is a direct sum. Any element is a sum, the finite sum of elements of the basis. Anyway. And finally, K-linear. So what you can correspond to K-linear? For example, the fact that you can see Nijk, as I already mentioned, as the K-dimension of the Hom space I already mentioned before. K-linear, so particular, every Hom space is a vector space. So as a K-dimension, so here you have this K-dimension for this Hom space here. Okay, and one other consequence, correspondence of K-linear is the Frobenius reciprocity, because you have something about matrices. Reciprocity can be reformulated in terms of matrices. Mi star equal Mi star, which mean dual correspond to adjoint. Dual correspond to adjoint of matrix. Okay, so so this was a bit too long. I'm sorry. Let me try to do something more nice. Okay. So let me put another color for something nicer. One like that, for example. Okay. Okay. So that's all for the introduction part. So we are done with introduction. With the introduction. Okay. Okay. Now we'll start a new section called preliminaries on monoidal category. Preliminaries on monoidal categories. So as I said, I will not recall the definition of a monoidal category. So you have details. You have associativity constraint, Pentagon axiom, unit axiom, etc. So I don't draw the pentagon with. So I already mentioned that several times in the previous semesters. But here I will recall by pictorially the notion of left dual, rigidity, dual of an object, of a morphism, and some lemma, in fact. So I will provide details from now because we will need explicitly these details for to prove the main result of the paper. Okay. So we need to recall some basic notion from monoidal category theory and graphical calculus. Call some basic notion from monoidal category theory and graphical calculus. Okay, the definition. So we will recall the definition of a left dual by picture. So let's see be a monoidal category. With unit 1, unit object 1. Okay. A left dual of an object X in the category of an object X in the category C is the data of one object X star and two morphisms, as I mentioned before. The data of an object X star together with two morphisms. And the zigzag relation together with two morphisms. So evaluation map and co-evaluation map. Fx x star tensor x to 1 co-ev x 1 to x tensor x star. So this one is called evaluation map. This one is called co-evaluation map. And the picture for these two maps is as follows. And co-ev equal like that. Okay. So which mean so here you have x star, x, and here 1, or here 1, x, and x star. Okay. So this picture is well defined. There is no confusion. You can surely, safely replace evaluation and co-evaluation because, in fact, in this definition, so co-evaluation and evaluation map should satisfy an axiom called zigzag relation, which is precisely satisfied by the picture. So satisfying the zigzag up to isotopy relation as follows. So identity. You have co-evaluation map, evaluation map identity. X to X. This is nothing but the identity. And the other one, identity of X star evaluation co-evaluation identity equal the identity of X star. So these two, so like that. Okay. So as long as when you have such zigzag in a pictorial calculus, you can replace it by a straight line. This is the zigzag relation. Okay. Now, so this is a left dual of an object. You have this one object X star, two morphism, evaluation and co-evaluation map, and the zigzag relation. This is exactly the definition of a left dual. Now you can provide the definition of left dual of a morphism. So let X, Y be two objects with left dual. In C with left duals. And we will consider the morphism between X and Y, and we want to define the dual of this morphism. So the left dual of a morphism F between X and Y of a morphism F in the home space, home set, in fact, between X and Y is defined as follow. So yeah. F star equal. So you have F between X and Y. You apply evaluation and co-evaluation like that. You get Y star, X star. You get a morphism in between Y star and X star. So here, our definition of a left dual of a morphism is just this picture. Okay. So it's very easy to reformulate this picture in terms of morphism, co-evaluation, evaluation map, identity, etc. Okay, so few straightforward through trivial observation. Observe by zigzag relation that two trivial equality. So identity of X star, so the dual of the identity morphism is the identity on the dual object. Okay, so you consider the identity. Like that. You apply the dual. Then, by zigzag relation, this is just like that. Okay. So this is trivial. Then, so the dual of the composition, you have to the dual of the composed morphism F with G is the dual of G composed with the dual of F. How to see that? So you compose F and G. So you draw F, then you apply the dual. So c'est X, Y, Z, Z star, X star. Then you apply again the zigzag relation, but in the other way. So you have F. So you have this one. So this is okay. This is as on the left-hand side. And then you want to replace this one by a zigzag. Here you have a zigzag. Okay. And then you have G and like that. Okay. This one to here. Okay, but this one is exactly what we expect. So this is exactly the F dual here, and this is G dual. And so you see, you switch you permute the order. You have G here, G on top, and now it's F dual which is on top. So this is exactly this relation. Okay. And last trivial relation is if F between X and X star, between X and X is an isomorphism, then F inverse star equal F star inverse. So wait a minute, I check something. So wait a minute, I have something to fix with my pen. Okay. Okay. So okay. What about that? So why this is true? So consider identity. Let me draw it in orange. Identity of X star is the identity of X star, which is so. Là, tu peux couper le son. Non, j'entends. Pas mieux dans l'oreille. Like that. So identity of X is the composition of F and its inverse. As we see before, you can transform the composition of dual of composition by the composition of dual like that, permuting the order. And that's all. So so you have this is inverse of this. So F star inverse equal F inverse star. Okay. So do we need to, maybe we need also to consider the other way, but it's the same. It is the same thing. So let me. Okay. Next. That's all for this trivial relation. So now let me state and prove something still straightforward, but not completely trivial. Lemma. So I wrote 2.1 because I may refer to it later. So let's see be a monoidal category. Let x, y be two objects with left dual. With left duals. Let f be a morphism between x and y. Okay. Then the following pictorial relation hold. So you start from the morphism f between x and y, and you apply some evaluation or co-evaluation, some co-evaluation. So now you have in x star. This is the same as considering the dual of f with this co-evaluation on the other way, on the left. Like that. So this lemma states that these two pictures are the same. And also like that with evaluation. So f star between y star and x star, you apply evaluation. This is equal to you have f x y star. Observe that here for the co-evaluation you have the f on the left, and for the evaluation part left, f is on the right. But anyway, we will prove the first picture and the second picture will be the same. Analog proof, same proof, similar proof. So, so consider this one. So it's still, the proof will be still easy. So, and here we will apply the zigzag relation. Y, x star. So zigzag relation. We have f x star and then the zigzag. Okay. But this part this part here is by definition F, the dual of F star. Whoa. Whoa, too much. So let me modify the size of the eraser. Okay. Okay. So as I said, this is the dual of F by definition. So you have F dual Y star X star, and the remaining part, this remaining part here, which is precisely what we wanted to prove. Okay. So it's too much. Okay. Oh, not Y star, just Y. Okay. So this is the first equality, and here, and the second equality, exactly the same idea. So the second equality is similar. Okay, that's okay. That's not too hard. This is straightforward. Let me continue with such straightforward result. Lima 2, 2. So let's see, be a monoidal category with a dual. Monoidal category with left duals. So by with left dual, I mean every object admits a left dual in the sense defined before. Then we can say something about the dual of the evaluation and co-evaluation map of an object. X, so Fx of the dual of Fx is coev X star. And the dual of coev X is the evaluation of X star. Like that. Okay, so that's pretty. So recall that so what I want to recall here? Okay, so because let me prove that in full details. So let me change the color for this recall. Okay, so recall that 1 star. So you can take the unit itself as its own dual object, left dual. Okay, take so you have 1 star as how to write, because then 1 star tensor 1 equal 1. So take evaluation map of 1 equal the co-evaluation map of 1 equal the identity of 1. Okay, that's okay. And then second recall, the dual of tensor product x, y is the dual of x tensor the dual of y. And you see that as follow, because you see that using the identity map, identity map of X tensor Y star is, as we saw before, the identity map of X tensor Y star, which is pictorially as follows. Which is equal to, so you have two identities. So you have identity X, Y, X tensor Y. And then you apply the dual homomorphism. You get Y star, X star, Y star, X star. And then you apply the zigzag relation. You get Y star, X star, which is the identity of Y star, X star. So this identity equal to this identity. So in particular, the object are the same. So X tensor Y star equal Y star tensor X star. Okay. So this is the recall part. Then, so what we want to prove is the following. Here. So start from that. So F X star. So the evaluation map. Let me draw it first like that. Then with the cup or the cap. So it starts from X star tensor X. It go to 1. Then you apply the dual. So what about that? So we know that the evaluation map can be written like that. So you have that here, X star X, and here, in fact, it is 1, but you don't draw it. This is a pictorial convention. So I put some dot to draw it from just here, but in fact you can forget about that. And here, this is X star tensor X. So you have two, the X star tensor X like that. And you have one zigzag relation to consider. You consider this zigzag relation. So you get like that. So this zigzag, this one is here. Up to, in fact, all this one is just this one. So let me draw to be clear. That just here. Okay. So X star, X double star here. And X star, X double star. Je me suis trompé de couleur. Okay. And this is nothing but which is the co-evaluation of X star. Okay. So it is straightforward again. You just have to be a little bit comfortable with the pictorial graphical calculus, but you see that the dual of evaluation map is a co-evaluation map of the dual object. And the second equality is the same. So we will shift a little bit the pose because I am. So let me just finish the proof and we will shift the pose of 1 or 2 minutes. So the second equality is similar. So the dual of the evaluation map of X is the dual of the co-evaluation map of X is the evaluation map of X star. Okay, so let me pause. Oh. Like. Okay, pause. Okay. Okay. So now let me define notion of pivotal monoidal category. Pivotal. So very important notion. So as I said, I decided to mention these details. I also mentioned this definition in the previous semester also, but we explicitly need this notion here to prove the main result. So that's why I recall that in details. So a monoidal category C with left dual duals is called pivotal if there is an isomorphism of monoidal functor between the identity functor and the double dual functor. It's pivotal if there is an isomorphism of monoidal functor between the identity functor of the category and the double dual functor. So let me reformulate this definition, which means, so such an isomorphism of monoidal functor means the following. There is a collection of isomorphism called pivotal structure AX between X and its dual, such that for all object X, so for all object X, Y in C, and for all morphism F between X and Y, so the pivotal structure of X tensor Y is exactly the pivotal structure of X tensor the pivotal structure of Y. So this is for monoidal. And for natural isomorphism, I guess, we get the following. F equal F inverse. So A, Y inverse compose F, compose F double star, sorry, compose AX. Yeah, double star here. So AX, the pivotal structure AX is is a morphism between X and X double star, an isomorphism. So we have that. So this is the definition. So this is the definition of what should be a monoidal functor between the identity functor of the category and the double dual functor. So let me draw a picture here. Picture. So the first picture. So we have AX tensor Y. X tensor Y and X double star tensor Y double star. So remember that if you apply X tensor Y star, you permute inside, but you apply double star, you double permute. So you get X star double star tensor Y double star. And so the picture here is as follows. How you draw the tensor product of morphism, you just put it together in parallel like that. X double star, Y double star. Okay, and the picture here is that F is, so you consider F, you want the double dual. So the dual one time, and again the dual, or double dual. And then you apply some pivotal structure here, AX, AY, inverse, X, Y. So this is a picture. So if you have such kind of spiral structure in the pictorial calculus, you can simplify it like that. Or if you want, you can put the pivotal structure on the other side. Anyway, you can do as you want. So this is a picture for the pivotal structure. Now, we define pivotal structure for a monoidal category with left dual. But in fact, the pivotal structure implies the existence of a right dual, which means that the category is rigid. Recall that the pivotal structure, pivotal monoidal category, is rigid. So existence of left dual plus pivotal structure implies existence of right dual. This is exactly what I mean here. Rigid, which means as left and right dual. And here, right dual, as you can expect, you put the star on the left, and this means you have an evaluation map prime X tensor right dual of X to 1. You have another co-evaluation map from 1 to star X to X, and zigzag relation. Okay. This is why. So why you automatically have right dual, because X is a right dual, according to the following definition, is a right dual of X star. So because it's pivotal, you have this identity monoidal functor between you have the isomorph. Sorry, because it's pivotal, you have a monoidal functor. An isomorphism of monoidal functor between the identity of the category and double dual. In particular, it makes sense to consider every object as a dual of another object here. And so, so every object can be modelized as a dual of such a dual, and X is a right dual of this one. So is it completely clear what I am saying? Yeah. So there is this isomorphism. So I have a little doubt here. Let me check. Anyway, it's not the point of this course. But I have a small doubt. Is it clear that according to pivotal structure, you always have, every object can be seen as a dual of another object? So I don't remember. I have a small doubt, so you should refer to the ECNO book to see the details about that. Anyway, so it's not the point here. We will not really need the notion of right dual here. Okay, in fact, in the book, they define pivotal. They started from right dual, from rigid. So they define left dual, right dual, and monoidal category with left and right dual is called rigid. And they define pivotal for a rigid monoidal category. But in fact, in the definition of pivotal, you don't need rigid. You just need with left dual, because we don't consider the right dual in the definition. That's why I define pivotal only for monoidal category with left dual. And I expected that pivotal imply rigid for monoidal category with left dual. But I have a small doubt, but it does not matter. It should be true, I guess, but it may require some few extra details which are not required in this course. Okay. Lemma, another lemma. 2, 4. Let C be a monoidal category. Monoidal category with left dual. Let X, Y be object in the category C. So what's the point of this lemma? So this lemma will be again an equality between two pictures. So we need to consider two morphisms. Let alpha be a morphism between Y and X star. Y, X star, and let beta be a morphism in between 1 and X. So then you get the following equality. And the following equality hold. Hold. So alpha of y x star x beta, and here 1. So there is nothing which means unit object 1 equal to. So the point is that you can move this one on the other side. Beta double star, but this requires to consider the double star of beta. Y x double star. Here, alpha y x star, and here, like that. Okay. Okay. And if the category is the monoidal category is pivotal, you can have something a little bit better. Moreover, if C is pivotal with pivotal structure, A, then so you have the following: beta x star x y. So you know you can replace the beta double star by a beta and a pivotal structure. Ax x double star alpha y star. Okay. So in fact, we will need such lemma. So I don't think I proved this lemma in the previous semesters. And we will need such lemma to prove one conjecture. So so one of the application, one of the content of this course is to prove one conjecture about the formula indicator. And the proof of that requires such details. So it's good to mention these details here because it's not so hard to prove. In fact, it's straightforward. You just need here to apply zigzag relation. So it's still very easy proof. So alpha y beta x. We want to put a zigzag here. So zigzag. So beta. Okay. So alpha. Zigzag. A zigzag. And then you continue. So we'll need more space here. Alpha. You have so y. So zigzag. So like that, that's okay. And here I need more space to draw the rest. And then you continue. So we just replace this part. Here we put this zigzag. And then you need to draw the rest. So you have the rest. Up. Beta. X. And you see, you permute the order using this zigzag. This zigzag allowed us to permute this order like that, which is equal to, and here, what do you see? You have to observe, you have a double dual of beta. Because you have, if you, one dual, a second dual, and again here, one dual, second dual. Okay, so you have double dual. So you can replace this picture by beta double dual. Alpha. It's still a straightforward relation, but it can be seen as a kind of magic. You started alpha on the left, beta on the right, and you finish with alpha on the right, beta on the left. So the trick was to apply this zigzag relation and to put beta inside like that. Okay, so now what about, so the pivotal structure, now it's done because we already know how to reformulate this in the pivotal structure. As we see here, the double dual with a relation between double dual and pivotal structure. And you don't need to consider the unit object. It's here. So now, by pivotal structure, if C is pivotal, then beta double star equal AX composed with beta. So A1 equal identity of 1, remember that. So, because we don't need to consider this part, here you have A1, so it's identity. No. You consider this equality, but you put this on the left-hand side. Yeah. And then what we will have here is identity. So this is exactly that. And so you just need to replace beta star here by that to get the end of the proof. Beta double star alpha y x star x double star equal, we have beta ax alpha y x star. And we're done. This is what we wanted to prove. Yeah. Okay, so it's okay. It's still easy, very easy. So let me mention here that in the rest of the course, we will mention some pictorial proof which are not at all easy. They are easy, locally easy. They are always locally easy. If you have a pictorial proof, you just consider locally the argument locally. It's always easy. But what I mean is that we will consider in the rest of the course some pictorial proof which are much more complex than that. And this will be, for me, a big challenge, in fact, to teach that in the sense of to draw the picture on the laptop. It will be quite challenging to me. Okay. So next lemma. So this lemma 2.4 will be used later in the proof of one conjecture, but it will be not today, in fact, not tomorrow, I guess. So we put this lemma somewhere in our mind, and we will recall it in few sessions, maybe 1, 2, or 3. So another lemma involving picture and the pivotal structure. So let's see, be a pivotal monoidal category. Be a pivotal monoidal category. Let A be the pivotal structure. Let X be an object in C. Then you have these two equality of picture involving the pivotal structure A. So AX star is morphism between X star and X triple star. So this picture equal, you can put on the right like that. A X inverse between X double star. So here is X double star. Like that, X star. And same picture for the co-evaluation with co-evaluation map. AX. Like that, co-evaluation map. X double star, X star equal A X star inverse. X double star. Okay. So we already saw something looking like that. Where? Did we saw that? No. Not yet. Okay. Yeah, here. Here. We saw something looking like that. Okay, but in fact, we will not apply this lemma just now. We will prove that directly using the result will prove about the dual of evaluation and co-evaluation map. Okay, proof. The evaluation map double star is the co-evaluation map of X star star. Wait, one too much. So you consider the evaluation map star, you have that, and then you add this extra star. And you apply it again, this lemma evaluation X double star. So this is the application of lemma 2.2. We mentioned before, we proved before here. So we apply one time that and then that. Okay, so we get that evaluation map double star is evaluation map of the double star of the object. That's okay. Next, the evaluation map double star of X composed with the pivotal structure X star tensor X is equal by the definition of pivotal to evaluation map of X. So evaluation map is a map involving a unit object, so we don't write it. And so we just apply this equality. One of the two pivotal structure is unit, is identity, so we don't need to consider it. And we get exactly this equality. Okay, and the other point about pivotal structure is it's monoidal. So X star tensor AX. Okay. So if you replace X double this one by this one and this one by this one, you get trivially evaluation map of X is evaluation map of X double star composed with AX star tensor AX, which can be drawn. So now we will apply this equality pictorially for our need. So we start from here. So now we start from that. So I will start from here, and we get that. It will be more convenient. So we start from that. X inverse. X double star. X star. Oh, not star. Like that. The evaluation map and X star. And here we have the evaluation map we want to replace. Evaluation map of X. Okay. So we will replace this picture by a picture for that. So it's like that, as follow. So you have so let me draw AX star tensor AX and evaluation map of X double star. This is precisely picture for this morphism, and then you draw the rest of the picture. X inverse identity here. X star, X double star. And now you simplify the two, one morphism and its inverse. So you simplify, they vanish. Simplification. So it is equal to just what remains, AX star, X double star. Okay, so this is what we wanted to prove here. Of course, the other one is the same. The proof is similar. So the proof of the second equality is similar. Okay. So this is not very beautiful. Okay, that's better. Okay. Now we will prove a relation between a dual and a pivotal structure directly without picture. So using the previous lemma. So I am still wondering whether we can prove that directly using this. In fact, if we apply F star, so we move so we have F on the left. Wait. So what we want here, F star. We have F star. So if you apply what we did here, we have AX inverse star. So AX inverse star is equal to AX star. Anyway, right. So let me prove that directly here. I don't remember whether we can prove it using the lemma 2.1, but using lemma 2.5, it will be immediate. So lemma 2.6. Let me check the time. Oh, it's almost time. Let me, for 2 minutes, I will just write the statement, and we will prove that tomorrow. So the same statement as lemma 2.5. Then AX star equal AX star inverse. AX inverse star equal AX star. And so, if you apply 2 times, you get AX double star equal A of X double star. And okay. So the proof will be tomorrow. If I'm not mistaken, yeah. So the proof will be tomorrow. So see you tomorrow. End of session. Okay. So you can stop here.